It's a pleasure this year to participate in this prestigious Terzaghi Lecture this evening. Instituted by the IFCEE Board of Direction in 1960, the Terzaghi Lecture was established by what is now the Geo-Institute to honor Karl Terzaghi. Annually, the Geo-Institute Board of Governors recommends a distinguished engineer to deliver the Terzaghi Lecture. As you can see from this slide, for more than 50 years, the Karl Terzaghi Lecture has been given by an individual honored for their exemplary contribution to the field of geotechnical engineering, and this year is no exception. I'm proud to be the one to introduce this year's Terzaghi Lecturer, Dr. Donald Bruce. Dr. Bruce has spent his career in the practice of geotechnical engineering, construction, and has produced engineering and construction, and has produced significant contributions to the profession that have helped advance our industry. I can think of no better forum for this speaker or this topic than here at IFCEE, where we have such a cross-section of the geotechnical engineering and construction community. Dr. Bruce's leadership in technologies such as anchors, micropiles, grouting, deep mixing methods, and diaphragm walls has shaped the way geotechnical engineers solve practical problems. He completed his formal education at Aberdeen University and then spent about a decade with Coalcrete Limited, rising to the seat on their main board. In 1986, he joined Nicholson Construction in Pittsburgh, Pennsylvania, as their technical director. Since the late 90s, he has maintained a technical consultancy, GeoSystemsLP, supporting consultants and contractors around the world. Throughout this time, he has been actively engaged in numerous professional and trade organizations and code writing bodies. In fact, he may be one of the most prolific practitioner writers in our industry. With nearly 300 publications to his credit, he has shared his experience throughout his career. He was recognized with the Martin S. Kapp Award and the Wallace Hayward Baker Award. And I think it is safe to say that without his efforts to expand our understanding of many geotechnical construction technologies, our industry would look very different. I'm happy to say that Dr. Bruce has been one of my mentors for many years, helping me navigate many technical and some not so technical challenges of my profession, or of the profession. So without further delay, Dr. Bruce, would you join me up here at the podium? Stay close to the microphone here.
Okay.
In recognition of your exemplary contribution to the field of geotechnical engineering, and in recognition, I recognize you as the Geo-Institute 2015 Terzaghi Lecturer. I present you with this award.
Thank you very much, Alan.
I very much look forward to your lecture, and thank you for your leadership in the profession. And it's all yours.
Okay. Well, thank you, Alan. Good afternoon, ladies and gentlemen. That was a wonderful introduction, only parts of which I wrote myself, but thank you as always. You see the list of the previous winners of this award already today, and when I think of all these famous people, I'm very humbled to be here today and to have been awarded this wonderful thing. I'm also very mindful of all the other tremendous engineers and colleagues who are out there just now who have not yet won this award. Please keep trying. It's important that you do. This award is by far and away the biggest and most surprising and wonderful thing that's happened to me in my professional career so far, and I thank you from the bottom of my heart, especially to Alan, who has been a friend of mine for many years, and to Billy Kemp, who was the previous president of the Geo-Institute, and in fact is the organizer of this wonderful conference that we're at. So my talk today is going to be in three parts, the beginning, the middle, and the end. Geologists always think in terms of three things like that. And so the first bit, I'm going to read some notes to you. The second bit, we're just going to make up as we go along. And the third bit, I think we'll just take it as it is, see how much time we have before dinner. As Alan described, the thesis of this talk is the evolution of specialty geotechnical construction techniques. And I'm going to try and introduce you today to what I call the Great Leap Theory. And each of these 3 photographs here in the picture demonstrates one of the 3 techniques that I'm going to talk about today, and we'll come back to that as the afternoon goes on. Now, of course, you obviously recognize some of the people in the slide, not that you've been to university with them or anything, but the gentleman in the upper right-hand corner is, of course, David Bowie. The gentleman in the lower left-hand corner is Jim Bowie, who fought and died at the Alamo in 1836, another great Scotsman. The gentleman in the upper left-hand corner is the great Scottish historian Thomas Carlyle, and it's really he that we're going to talk a little bit about for a moment. The gentleman, of course, that you'll recognize from your textbooks in the bottom right is, of course, Professor Karl Terzaghi. Now, between 1858 and 1865, Carlyle wrote a 6-volume opus on the life and times of King Frederick the Great of Prussia. The work had followed his 1841 masterpiece entitled On Heroes, Hero Worship, and the Heroic in History. In these publications, Carlyle developed what we now call the great man theory of history. This states that the history of the world is but a biography of the great man. He evaluated the hero in different guises: as a prophet, Muhammad; as poet, Dante and Shakespeare; as a pastor, Martin Luther, John Knox; as a man of letters, Samuel Johnson, Robbie Burns; and as king, Oliver Cromwell and Napoleon Bonaparte, kings, paradoxically, in all but name. With time, at a different time, Carlyle could doubtless have explored the hero as a warrior: Admiral Lord Nelson, General Stonewall Jackson, George Patton; or the hero as the musician, as David Bowie wanted to be in 1977. It's probably the first time that David Bowie, Jim Bowie, and Professor Terzaghi have been seen on the same slide. Now, all of us here today are engaged in some aspect of the broad field geotechnical engineering, a discipline barely embryonic in Carlyle's time and bound primarily to the demands of military engineering. We can be convinced that the great man theory works well when considering the more fundamental and theoretical aspects of our discipline, such as rock and soil mechanics. There's a wonderful continuity in this little argument I'm going to present here. Professor Dick Goodman, who many of you know, is widely regarded as the father of modern rock mechanics. He remains a gifted engineer and a thespian. Arguably, his finest and most enduring work is his 1998 book, Karl Terzaghi, The Engineer as Artist. Professor Goodman dedicated this book, in turn, to Ralph Peck, whom he called a courageous, strong, honest human being whose teaching, writing, speaking, and practice of civil engineering continue to light the way. Dr. Peck, in turn, is quoted in the book as follows: "Although I knew Terzaghi well, because he'd worked for and with him for almost 30 years, I did not fully appreciate the personal struggles of the genius of the man until I read Goodman's manuscript. Goodman has caught the essence of the man." Dr. Peck gave the first Terzaghi lecture in 1963. Terzaghi, Goodman, Peck, not to mention others of such status, such as Arthur Casagrande and Mike Duncan, the Terzaghi Award winner 1991. These are great men in geotechnical history, bringing enlightenment, inspiration, and example to all of us that they touched. Now, each of these men, as you probably know, spent as much time in the field as they did in the classroom, and each was, of course, intimately acquainted with construction, means, methods, and materials. They solved, in a practical way, otherwise intractable construction problems and had the gift of communicating simply and clearly the logic and details of their solutions. None of these men, nevertheless, was a contractor. I guess everybody cannot be perfect. Now, my thesis is that in specialty geotechnical construction, the great man theory does not prevail. Instead, it is clear to me that the Great Leap theory has been at work. Great Leap theory simply states that the technological developments in specialty geotechnical construction are not incremental or slow or progressive like the aging of a really good scotch. Rather, evolution occurs in discrete and startling leaps, triggered by the demands of one special project or group of projects. Obviously, there's an integral place of honor for those behind the controls, especially entrepreneurs with the vision and the courage and the confidence to try new things. And in this category, our late friends Arturo Ressi, Dennis Milgard, Wally Baker, Fernando Lizzi, Harry Schnabel, and Tony Barley spring easily and yet very sadly to mind. Fortunately, others of this ilk remain with us, still pushing the borders, breaking the paradigms to develop new and improved techniques and processes. Many of them are recognized in the course of this talk. Okay, so the guessing game continues, and we still have Thomas Carlyle, we still have David Bowie. That's Stonewall Jackson in the bottom left, and unfortunately that is Napoleon Bonaparte on the bottom right-hand corner. So, to constitute a great leap, I propose that 6 successive criteria need to be satisfied. And please try and remember these as we go through the rest of the afternoon, because each of the 3 techniques that I'm going to talk about, we're going to demonstrate how great leap theory is satisfied by looking at each of these 3 successive steps. So, criterion 1, the project, group of projects, or application must be of exceptional and or unprecedented scope, complexity, and construction risk. Criterion 2, a specialty contractor must exist who has the ingenuity and resources to devise the solution, and there must be a manufacturer that he can work with that can provide the equipment that he needs to implement the solution. Number 3, on the other side, there must be a responsible individual and or agency on the project owner's side who is prepared to take the perceived risk of deploying a new technology or technique, and who already knows the answer to the question. So where has this been used before? There's got to be somebody on the engineer, the owner's side, that is willing to take that risk. Criterion 4, the projects that we talk about have got to be successful. This is clear. We cannot have a recurrence of the situation where the operation was a great success, but the patient died. So it has to be a good job or series of jobs. Number 5, to qualify for the Great Leap. Details of this project must have been published widely in the scientific technical press, and not just or only as wonderful articles in the trade magazines, no matter how beautiful and informative these may be. And then number 6, within a few years, there must be some formal codification or other influence over construction processes to assure the legacy of the Great Leap and to guide and tutor future exploitations and the dubious defense of patents notwithstanding. In our field, such recognition typically comes through the publications of a federal agency, such as the U.S. Army Corps of Engineers, Bureau of Reclamation, Federal Highways, and so on. A professional society, such as the Geo-Institute, or the efforts of the trade associations, such as DFI, ADSC, or PTI. The Great Leap theory can be elegantly demonstrated by analyzing progress in a limited number of specialty construction processes. Professor Terzaghi is now joined on this slide by Admiral Lord Nelson in the top right and Warren Zevon on the bottom left. And Natalie, that one's for you. You got it. So for this demonstration, I've chosen 3 processes particularly close to my experience and to my heart. I apologize to those of you in the audience whose particular field is not covered, such as ground improvement, the whole wide world of large diameter piling, even anchors, my PhD subject, or micropiles, where Alan and I have worked so closely together over the years. So the 3 that I intend to talk about, and those of you who know me will not be surprised, grout curtains and rock for big dams, cut-off walls for dams, deep mixing methods. And again, I do apologize that your own particular favorite subject has not been covered, but I would encourage you that if you are moved, why don't you write a similar paper about the great leaps that have influenced your particular technology as well. Now, I have to come with a government health warning here. In the course of the next half hour or so, I'm going to be mentioning a lot of companies, contractors and consultants especially, with whom I have worked over the years and who are integral to the Great Leap theory, i.e. Criterion 2. So I'm not trying to promote them or endorse them or say that they're the biggest and the best. I'm simply making a historical statement of fact. So please don't not buy me a drink in the bar later if I don't mention your company. Okay. So with that in mind, then we go to the fun part of the lecture. So this is where we're just going to make it up as we go along. And I have my board in front of me, and so I don't have to turn sideways. And at a time like this, and especially before dinner, beginning of a conference like this, I don't think it's just satisfactory that you be educated. I think it's important that you be entertained as well. So those of you who have come here with your notebooks ready for fourth-order differential equations will be sadly disappointed. Those of you who would really like to see, thank you very much for that. Right with you, brother. Those of you who are here maybe to look at some cool bits of equipment, nice jobs, some of whom you may have been involved with, that's the kind of talk we're going to have for the next half hour or so. So, grout curtains and rock. And remember, we have 6 criteria that define the Great Leap. And the first one is that the project's got to be exceptional. And right away, we say here that there's a group of projects that kick-started the Great Leap in curtains and rock. And they were a group of projects from 97 through to 2007 involving deep remedial curtains and karstic limestone. Now, those of you who do not have and have not had the pleasure of working in karstic limestone, a few words. Limestone has joints in it. Over the years, these joints erode, create caves. Karst is a word in German associated with cave. And so many of our dams in and around the Mississippi Valley are sitting on karstic limestone. Most of these big karstic features you can see on the left-hand side here are clay-filled. And so with time, as the reservoir works on these features, if they haven't been previously treated, this material will erode and will cause a dam safety incident. And we're not just talking about wee dams or little dams. We're talking about gigantic, big dams. That's why we're the conference on large dams. It's not a conference on little dams. It's a conference on large dams. And so we have dams that are hundreds of feet high and thousands of feet long. So in drilling and grouting, the pre-leap practices, this would have been the state of affair from maybe 1900 through to about 1985. Very prescriptive specifications. Complete absence of rational design and acceptance processes, and a widespread use of rules of thumb for design and execution. And from the technical point of view, these would have been the features that marked the kind of work that was done until quite recently. And all these, incidentally, are bad things, okay? So even if you don't know about drilling and grouting, just assume that this is just not good news at all. And especially the last one. Many of our dams that we work on, for example, in the Tennessee Valley Authority, back in the day, were unsuccessful because they were grouted not to a residual Lujan value, but to a residual dollar value. And so basically you stopped when the money ran out. And when you grout in karst, you've really got to know what you're doing. So these archaic processes completely unsuited then to the demands that we faced in 1997 onwards. Now this is a lovely photograph given to me by my friends in the California Department of Water Resources with whom I work. And I am not picking on you guys. I'm not picking on you, just that you have good photographs. So back in the days when we still grouted in black and white, you can see that this would be a typical site setup. Now, to illustrate the mentality of the day, I put up this quote, which I'll just give you a couple of seconds to work your way through. And as you're doing that, the commentary is that Polatti was an extremely well-recognized and revered dam grouting engineer in the US. And so he's been asked to give this state of practice, right? And he's saying, in preparing this paper, I've requested copies of specifications from all these people. And I've compared that with all the stuff that's 30 years old in my files. And I concluded that we in the United States have not, in general, changed any of our approaches on grouting. And this is good. He actually stood up and said this. And it's a remarkable commentary. And then, of course, he goes on to talk about difficulties in having flexibility in the field. And then problems communicating and training. Gosh, what do you expect if you're working in Gothic script on your specifications? Now, criterion 2, the availability of the technology. So right up until the 1990s, those of you who are in manufacturing and equipment supply will know this, there was a large momentum against new technologies. The notable exceptions were some of the US Army Corps of Engineers people, some of the reclamation people, and Hayward Baker, who promoted early computer-grouted monitoring at Ridgeway and Upper Stillwater. And back in the day then, there was the initial promotion of gin theory by Lombardi and Professor Deere. So not much happening. Then the leap occurred. And this is where we have our first confirmation that there's a technology available to solve these problems. And it was basically an association of a contractor, Advanced, and a consultant, Gannett Fleming. And they got it together. So they introduced simultaneously numerous technical developments as an integrated package. So from the design side right through to the implementation side. And I think, quite frankly, they hit the sweet spot in the market because the Corps especially was moving towards best value as opposed to low bid contracting and more performance-based specifications and therefore more ability for the contractor to actually give what was in his mind as opposed to just his arms and legs. He was able to take his head to the game as well. And you can only do that if you have performance-based specifications. So all these improvements come along. Design improvements. There's no such thing, folks, as a one-row grout curtain. It's an absolute fallacy. It's like the check is in the mail and other ruder comments of similar nature. Inclined holes, not vertical holes. The depth of the curtain being dictated by the geology, not by a rule of thumb, and various other things as well. And then once we had built the curtain, verifying the residual permeability of the curtain by doing in situ water tests. So instead of grouting to the dollar or the sack of cement, we're grouting to the Lujan value or the centimeter per second. So that's on the design side. That's what the Gannett Fleming team brought. Advanced, what did they do? On the drilling side, they commissioned and had built for them a new generation of drilling rigs specifically targeted for the deep grout curtain market, the Cubex company from Winnipeg in Canada. At the same time, we were looking at ways to drill through our existing dams without causing damage. And so we had the sonic drilling that was first proposed by ProSonic and Bort Longyear. And then we had the double head dry duplex system for overburden drilling as developed by Advanced themselves. Increasingly, from McCook Reservoir in 2003 onwards, the water powered down the whole hammer, produced by Wasara from Sweden. And this is absolutely the bee's knees in terms of rock drilling, combining rotary percussion, i.e. speed, and water for flush and cleanliness of the fissures. We don't drill with air when we're trying to grout fissures. And then, of course, the routine use of automated MWD, measurement while drilling techniques, such as offered by Jean Lutz and many others. Of course, other companies, such as Bauer and so on, have their own drilling performance measurement technique. But fundamentally, Lutz came with the first one, and others followed and improved upon it. And then we have another really interesting thing that's happened over the years is the systematic use of borehole deviation monitoring, and specifically using the Robertson geologger and other devices as well. It's really quite important to know where these holes really are 400 feet down. So again, we are picking on California here. So here's a lovely shot of some of the early drilling and grouting work that was done on the Oroville Dam complex in the northern part of the valley. And you see these gentlemen in the aluminum helmets on the left, and that's a typical frame-mounted rig, air-powered rotary head, good to maybe 50, 60 feet depth, and who knows what kind of variation in inclination at depth. And in the background, you see another one of these little rigs. We fast forward then to my early years in concrete that Alan mentioned, and this is a photograph taken on the summer day in 1978 in Scotland. And this is the foundation preparation at Kielder Dam, just on the border there where we keep the English out of Scotland. Then, of course, there were other staggering breakthroughs in drilling technology. I was really trying to get a photograph of the guy in green underpants since it's St. Patrick's Day, but unfortunately, we'll just have to do with the blue. But he's got his hard hat on, so this is good. And then for those of you who are really into health and safety, this is rather good. Here we have this gentleman in Tarbella Dam sitting on top of the drill head, helping to unscrew the rods as we're changing. So yeah, it's funny, but it's not to be done. So here's then what we do now. And this is a photograph of one of the Cubex rigs that was used by Advanced and Gannett Fleming at Wolf Creek. And many of the other contractors in the room, Baker and Nicholson and so on, have these wonderful machines now. And they really have set the standard. Climate-controlled, automatic drill rig parameters, automatic rod handling and changing facilities, tremendously adept, huge productivity improvements over the last. And here's our friend Mark, and he's looking at the business end of the double head dry duplex system at Clearwater Dam. Then we have again the water-powered down-the-hole hammer. Many of you know what the normal air-powered down-the-hole hammer is. You can see the gentleman in the top left there, and that's typically the size. What's that, a 4-inch hammer maybe? But instead of it being powered by compressed air, these hammers from Wasera are powered by water. Water is a non-compressible material, and therefore it's very much a kindler and gentler way of drilling holes, especially in delicate conditions. So even though we use high pressures to activate the hammer, as you can see on the top right, the flush water just wells gently out of the top of the hole, and that's one of the great advantages. Monitoring while drilling, these Jean Lutz systems that monitor everything that happens during the drilling of a hole. So you don't really then have to think about drilling a site investigation hole adjacent to work out what the strata are. And so if you were faced with this log here, you would look at these different colors, you would look at the different parameters that they represent, and convince yourself that there's something funny going on, let's say 60 feet beneath the surface. So every hole that we drill on a dam or any construction site with even destructive drilling methods is a source of information on the ground. It's not just a means of getting a hole in the ground. It is an investigation and a verification of the ground as we go. And so often, especially as contractors, we miss that because we're so busy getting footage, we forget about what the footage is telling us in terms of what the ground is doing. Here's this lovely instrument, the Robertson Geologger, and basically it's an optical television machine, and it goes down the hole, and it gives you the equivalent of a flat core. So instead of having to drill a core with a different drilling rig, take it to the surface, have a look at it, you now have an optical, basically a three-dimensional appreciation of the in situ conditions in that hole. And so if you're really clever and you can manipulate this, you can work out the orientation of defects and so on, which is very difficult with conventional coring. Injection systems. What else did Advance bring to the table? Well, they brought grout buggies. So what? But I'll show you in a minute. Automatic grout mixing, weatherproofed enclosures. Grout mixes. All grout mixes are not the same. And so my old colleague Alex Nauts in Canada was the first person in North America to introduce the balanced, stable, multi-component grouts. And these give superior rheological as well as stability properties. They're not thick mixes like some people think that we have to inject at huge high pressures. It's not the case. We're getting the best of all the worlds rheologically, from a hydration point of view, and so on, by having a whole series of components, just like making a cake. And depending on who's coming for dinner, you have a little bit of this and a little bit of that to give you the desired properties. And then we have this whole issue of pressure filtration coefficient. Now, De Pauli and I wrote a paper back in 1992 that nobody read, which is not surprising, except for Alec Nauts. And he picked the bones of that. And so he fully understood what we were talking about. And I'll show you what I mean in a second. So here's back in the black and white days. There's the fellow standing over, in fact, it's a concrete mixer, feeding an agitating drum, feeding the pump, and he's got his spaghetti of wires everywhere and hoses everywhere. So that's typical, again, of the practices right up probably in this country till the early 90s. And then we moved into color, and here is a photograph that I took in the mid-70s, and still, it's not great. Distinct absence of hard hats, PPE, It's open to the weather. It's really a bit untidy, but at the time we thought this was great. Now, of course, it's a wee bit different. And we have electronics, we have flow meters, we have sensors. The thing in the top right there is the GROUT buggy. So this is an automotive machine that runs around the site, has the hydraulic reel, drops the packer and the hose line down the hole, and has all the sensors on it. So basically, it's relaying in a telemetric way all the information about the ground injection instead of having guys all over the place looking at gauges and trying to record it in a wet notebook. Now, this is as complex as my talk gets today, but it's fundamental. And this basically explains the whole background to balanced, stable grouts. And many of you have seen this slide before, but I don't know if many of you really understand what's going on. It took me a long time to work it out as well. But along the bottom, you've got some measure of thickness, if you like. So very thin on the left, thick grouts on the right. On the vertical axis, there is a measure of stability of the grout under pressure, meaning that when you start injecting it into a fissure in situ, what is the measure of that grout to hold itself together as opposed to just pushing the water out of the mix and smearing off the borehole wall? That's called pressure filtration. Well, in the early days of dam grouting, everybody knew that the way to get grout in the ground was to put a lot of water in the grout. That made it nice and thin, so you could therefore inject it further. But that was absolutely the wrong thing to do. So we had very low cohesion, but we had enormously unacceptable pressure filtration. You can see the black line in the top left. And that just meant that all these dam grouting jobs that were done were pumping water into the ground. The cement was smearing the inside of the borehole. And because we couldn't get a proper reduction of takes with time, these guys ended up back in the day with holes at 9-inch or 6-inch centers to try and get refusal. And it was simply because the holes were not being used efficiently because the grout was wrong. Now, our friends then in Solitanche and Rodeo in particular, and also in Bar, began experimenting back in the 40s and 50s with the use of bentonite, sodium montmorillonite, to stabilize the grouts. And gradually, we could reduce the pressure filtration, which is good, but the penalty, of course, was to make the grout thicker, which made it more difficult to pump, and it wouldn't spread so far in the ground. So then the gift of the multi-component grouts from the mid-80s onwards was to come back down that curve, down towards what we call high-performance new grout mixes. So they are very stable, so we grout them, we put them under pressure, but they don't break down, but they're also of very low cohesion. So once we get amenity into a fissure, the grout will then travel until we run out of energy. So that, in fact, is the essence of these multi-component balanced stable grouts. It's terribly important. Now, computer control and analysis. Those of you who know me would understand that what I know about computers you could write on the back of a postage stamp with a big felt tip pen. But as a user of these technologies, I'm all for it. Now, one of the first techniques that was developed after Hayward Baker's initial attempts was called CAGES, Computer-Aided Grouting and Evaluation System. And this was developed by ECO and Alex Nauts up in Toronto. Soon, as a result of our work at Penn Forest Dam with Gannett Fleming, they developed a superior system, or a different system, called IntelliGrout. And basically, this was recording, analyzing, controlling, and displaying all injection parameters in real time. And this allowed then apparent Lujan theory, which allows us to bring holes to proper refusal, to be adopted. And again, Alex was behind that. We used IntelliGrout in real time in order to demonstrate that we could grout to a Lujan or half a Lujan via systematic use of multi-pressure Lujan testing. And then the optical televiewer to show the in-situ rock conditions in the curtain without having to core. So we save the whole expense of a separate rotary coring machine. So again, just some slides to accelerate us through this process here. But here's dipstick, gauge, and stopwatch technique. And this guy literally is using a dipstick to try and measure the amount of grout in the tank and therefore how much grout has been pumped. And that is a photograph from the 1990s, folks. This is what our friends in Gannett Fleming would call level 3 computer monitoring system. And it's not unusual to find contractors, now the superior contractors in North America, having similar setups on their projects. And what are we looking at? Well, typically, the key things are the flow rate, the top graph, We want to see that coming down as we grout the slide, as we grout the stage rather. And on the bottom axis there, the horizontal axis is time. This system will display gauge pressure as well, but then these two upper curves are integrated into the lower curve, which is the apparent Lujan curve. And so as a grouting engineer, you're sitting watching the TV, and you're guiding the injection of any one stage to ensure that the residual apparent Lujan approaches zero. That means there's no take in the hole. So this is how we do it now with apparent Lujan theory. Now, there are other ways, like GIN method and one or two other things that Golder have introduced as well. But in essence, most of the superior work that's done in the US runs off apparent Lujan theory. So the third criterion, what did the owner think when all this came up? Well, the first two projects that were done with these great leaps were both private jobs. Penn Forest Dam, city of Bethlehem. Hunting Run Dam was the county of Spotsylvania. They and the engineer of record accepted and shared the novelty risk. There had to be somebody who would dive in the pool first. And then equally later, our colleagues in the Corps accepted the novelty risk, and particularly some districts, Louisville, Little Rock, Nashville, Chicago, backed up by headquarters in DC. Now, the one thing that you see in common with all these districts there, other than DC, is basically they all sit on karstic limestone. So they had the problem. They had to solve it. But they showed great courage and great resolve in accepting these new methods. So were they acceptable? Did we have success? Well, sure we did. That's why I'm going to talk about them. And so we grouted these to very tight residual permeabilities, 1 to 5 Lujans, depending on the target. Grout curtains were used systematically, have been used as part of what we now call composite walls, where we do drilling and grouting to begin with, and then we follow up with a diaphragm wall between the two grout curtain rows in order to prevent long-term degradation due to the movement of the karstic material. Technical publications, the fifth criterion. Have we published anything about these things? Well, you bet. So we've had a couple of really good conferences, New Orleans in 2003 and 2012. The annual conferences of the Dam Safety Association and USSD have tons of papers on this kind of work. There's a couple of textbooks, blatant advertising there. And every year we have the annual short course on grouting at the Colorado School of Mines, at which many of you in this room systematically teach at. And of course, presentations at the Corps' infrastructure conferences on an 18-month cycle. And as I say before, we've mentioned a couple of contractors in particular, but this is now the standard of care of superior grouting in North America, and it's attracting attention on a worldwide basis. Have we codified it? Yes. Those of you who are interested in this work will be glad to know that Gannett Fleming, under contract to the Corps, have now completed that revised grouting technology manual, and that's going to be, well, has been issued as of July 31 last year. So it's a tremendous piece of work, and grouters all over the world, just like Sam here, are undoubtedly tickled pink to have that on their bedside table. Now, the second group of technologies that I want to talk about are cut-off walls for dams. And here's a rather good photograph of Wolf Creek Dam in Kentucky, and a little bit of information about it. But you can see right away the problem that's incipient in the foundation. And that red circle identifies a man. And so that cave in the foundation of that dam is approximately 30 or 40 feet high. And that is the condition that the dam was subsequently built upon. Back when these dams were built in the 30s, 40s, and 50s, our government agencies did a tremendous job preparing the foundation. But here there was a design flaw in that, having cleaned this foundation, having taken the clay out of these features, the Corps then replaced that material with clay, which was not really a terribly good idea. But the thing was that this dam, Wolf Creek, was designed in the 1930s and started work just before the US joined the war. And then it was suspended. So by the time it was finished in 1952, you were basically looking at a design that was 20 years old. And in that period, a lot of things had happened. So guess what? Here we have severe hydraulic distress after the first. Here we have hydraulic distress developing. So we've got a wet area under the dam. and a slowly developing sinkhole or two right there, which is bad news. Those of you who work in dams know that anything like that is just simply bad news on a big dam. And then, of course, the infamous muddy flows. So this is not good when you have a dam that is holding back Lake Cumberland and is protecting Tennessee. The primary mode, the failure mode, of course, was related to the erosion and the piping of the soft material and the clay backfill. And so back in 1975, the IFCEE Corporation, under the leadership of Arturo Resi, won an international competition to build the first ever cutoff in an active dam anywhere in the world. And this is a photograph from the 75 effort. And this is exactly what they did. There's the IFCEE wall in purple. In fact, they had a wall running through the axis of the dam, and then another smaller wall down in the switchyard. But the Corps had actually saved the day in Kentucky in 1968 through 73 by doing all that grouting to repair the damage before the wall was built. So that was how the original wall was built. It basically used rotary drilling techniques, not secant piles, but large diameter piles, and then that green bit being taken out by a clamshell guided by the adjacent secant piles, by the adjacent large diameter cased piles. So it was a tremendous achievement that was done. And these are photographs from the 70s showing the equipment, showing these cased piles, and then showing the very sophisticated deviation monitoring device on the right-hand side. But it worked, and they built the wall 24 inches thick, thousands of feet long, 280 feet deep, 97 million back in the 70s. So it was an absolutely spectacular project. However, Dr. Peck was on the original board of consultants. Many of you will know this, as was Mike Duncan. And he thought at the time that the wall was neither deep enough nor long enough. Was Dr. Peck ever wrong? And by January 2007, Wolf Creek was judged to merit what we call a DSAC 1 rating, i.e. get something done right now. And there was a justification because of the return to the classic distress indicators. Now, for those of you who don't know about dams and distress in dams and so on, lots of things can happen. You can get sinkholes, you get wet areas, you can get seepage, you get artesian conditions in the piezometers, you get cracks in the roadway, you get settlement. And all these things were in the red zone as far as Wolf Creek in late 2006 and early 2007 when we caught it. So there was a phase 1, and it was conducted by Advanced and Gannett Fleming, emergency grouting operation, but the intention of the Corps was always to build another diaphragm wall. Longer, deeper, better, more expensive. So the Corps, again, very prescient, and released the work on a performance-based spec, emphasizing dam safety in every process of the work, as well as urgency. And this is a classic example of one of these great leaps in business. Now, this problem attracted international interest. Our colleagues in Germany and France and Italy were equally as interested as were our US companies. And it was obvious to everybody that what had been used and done back in the 1970s was not going to work the second time round. And so a lot of new things had to be done. So this was the solution conceived simplistically by the Corps of Engineers. So here's a cross-section of the dam sitting on soil. That was the other thing that we didn't do back in the 50s. We didn't strip some of the soil. And then the karstic limestone. And these browny yellow things are big karstic features. So here's the wall, the existing wall built by IFCEE in the 70s. And this is what the Corps wanted to do this time. Deep grout curtain. And then between the two lines of the grout curtain, a deep diaphragm wall. So you can see it was built on the downstream side to save quantity, and it would completely negate the purpose of the first wall. So that was what was planned. And just to summarize again, There's the wet areas, there's the muddy flows, the sinkholes, the existing wall that was done by ICOS, and then here's the new wall that is upstream, longer, and deeper. And I'll come to the protagonists in a minute. So who are they? As you know, the job was done by Trevi Solitange joint venture. Who are Trevi? Well, they had acquired the ICOS company in 1997, and so they had the mentality of what had gone on at Wolf Creek first time round. They also had picked up Rodio, who were a very fine Italian company at the same time. They had very good and similar experience at Walter F. George Dam in Alabama. We'd also worked, as Nicholson, we had the joint venture with them at Beaver Dam in Arkansas, building a secant pile cutoff. Because of their other work, they had also particular experience in directional drilling and in water-powered down-the-hole hammers. Solitange, so who are Solitange? Right? One of the great companies. Pre-war French subsidiary of Rodio. And of course, during the war, they were French, therefore they won. Rodio were Italian, and unfortunately, they had lost. And so after the war, basically, Solitange became the dominant player in the whole Solitange-Rodio empire. And then, of course, Solitange combined with Bechy some years ago. But the key thing that Solitange brought to the table was they had patented in 1972 the hydrofreze, or hydrofreze, with apologies to my French friends, also known as a cutter or a mill, and produced by subsequent competitors. Now, what's so special about a hydromill? Well, this is literally the bee's knees. This is a big frame that you aim at the ground, you turn on the wheels, you turn on the pump, and this machine chews itself into the ground, creating a wonderful, straight, regular slot. And if you do that enough times, you create a diaphragm wall. So it's very simple. That's as complicated as it gets today on the hydromill. So according to the information that Tom Richards gave me, it was initially deployed in Paris, 1973, and it was used for the first time by Solitange on a dam for remedial purposes at St. Stephen Dam, South Carolina, in 1984. So Solitange had a very long track record working on dams in the US. Thereafter, it's been used by many other contractors, such as Bauer and Bencor and so on 8 other major dam remediations prior to 2008. A lot of work. And if you were able to read this, this would show that since 1975 through to 2005, there's probably been about 21 or 22 major jobs done in the US. And I think it's the blue highlights those jobs that were done using the hydrofreze. So right up until 2008, a pretty steady 1 or 2 dams a year in the US. Many of these projects, say, done by Trevi's partner at Wolf Creek. The deepest wall that had been constructed before Wolf Creek was, in fact, at Mud Mountain Dam, over 400 feet deep. And most recently, we hear from our friends in Italy that they have now taken this to 800 feet at Gualdo as a test and achieving 0.13% verticality. So basically, the hydromill allows you to drill very deep into hard material and guide it to a fraction of a degree of verticality. It's an extraordinary machine. I always used to describe it as like a Formula One racing car, that when it worked, it went very fast, but it would spend a lot of time in the pits. But more recently, the hydrofrezes, the hydromills, have become much more reliable from the technological point of view. So, obviously, Trevi and Solitange get together to do Wolf Creek 2. And how do we design that? Well, first of all, we're going to build a 6-foot wide disposable diaphragm wall through the dam itself to protect the dam from the effects of the rotary drilling underneath. So it was a very clever concept. And this is what, in fact, was done. So here's a little animation just to summarize better what I just said to you. So we've got the embankment, the poor stuff, and then the rock. Here's the center line of the wall. First thing to do is to do the drilling and grouting of the rock on either side. Remember, this is a composite wall. So what we're trying to do is to prepare the ground for the diaphragm wall. Then the interesting thing that the joint venture did was then elected to do an LMG operation to treat specifically the interface between the dam and the rock to further protect the ground for the installation then of this 6-foot wide diaphragm wall, which was taken down just to the contact. Having protected the dam, the next stage then was to build the cutoff in rock. And this was achieved with, first of all, directional drilling, and then following up with, I think, 50-inch holes at like 30-inch centers to create a secant wall in the rock under the dam having been protected by the big diaphragm wall. Hayward Baker were engaged to do that LMG work. They completed also the HMG work that had been begun by Advanced and Gannett Fleming. Many of you will have seen these slides already, but there was a lot of iron, as the contractors say, on this job at any one time. So here's the big 6-foot wall being constructed in the foreground. Then you can see the directional drilling, the Solmec machines in there, controlled to within 0.1% accuracy at depth of almost 300 feet. And then the Verth pile top machines installing the secant piles through the wall and into the bedrock to create the cutoff. So here you have 50-inch piles at 31 or 35-inch centers. Maximum depth 277 feet. Okay, so that was the contractor side, right? Criterion 3. If you were the owner, would you have accepted it? I would have been scared witless, quite frankly. But let's remember the Corps was very brave back in 1975, and its board of consultants were very brave. And effectively, although flawed, that original work bought 30 years of dam safety to the Corps of Engineers. And I think that the Corps and the 2007 board were no less courageous in designing the second wall, given their superior knowledge as to how fragile that dam really was. It was just on the edge. Now, the Corps didn't go into this blindly, and they put a lot of risk mitigation measures together. So they awarded this job on the basis of best value as opposed to low bid. Focus on the technical proposal, very important. First, before we could move into the production phase, we had to do technique demonstration areas, full-scale tests on site to show that we could do the work and do it safely. Very high levels of QA/QC. Contractor's side and the Corps side each had over 30 people full-time on QA/QC every day. Implementation of a very intense instrumentation monitoring plan to make sure that the dam was monitored during its penetration and during its remediation. And then there was actually very effective partnering. Partnering is often something that people turn their noses up at, but partnering was essential to the success at Wolf Creek. And not only did the two sides get together, but the Corps had its own board of consultants, but the contractor also appointed its own equivalent board of consultants. And so they got together at different levels. And so, especially in the early days, when things were maybe a little bit hairy from different points of view, there would be these massive technical meetings at which many things were thrashed out over a couple of days. And to the great credit of the contractor and the Corps, that these things went very well. So sure, as you all know, it was a success. Only one of 1,197 piles went outside the verticality criterion. Everything else was satisfied, without question. The job was finished early. No dam safety incidents. But I will say that when you drill with the water hammer, when you do grout with the HMGs, you will have transient pressure spikes in the piezometers. These happen. But as long as they're transient, your dam, which is 300 feet high and 6,000 feet long, is not going to feel them. So we're not going to explode the dam or hydrofracture it like some people think that don't fully understand what we're doing. Since then, all the indications on the job are that the dam and the foundation are functioning very efficiently. It's been a beautiful and extremely well-monitored project. So, have we published? Well, you bet. And so, there's been at least 12 technical publications so far in the usual suspect conferences. It's been published all over the world, Europe, US, and South Africa now as well, I understand. The Corps and the contractors have really put together a lot of very good reports that are available to you. And codification, sure. The Risk Management Center of the Corps of Engineers, headed by David Paul on an interim basis, is producing an engineering manual on cutoff walls for dams and levees. And this will enhance the existing EM. And that's going to be published later this year. Reclamation, my friend Mark Bliss, is also finalizing a new design standard on cutoff walls to be published later this year. The DFY Slurry Committee Gianfranco De Chico, who I believe is here, developing a similar guideline. Gianfranco's a wee bit further behind on schedule, but that is apparently going to be ready to go next year. And all of these publications will give new blood for the existing ICOLD Bulletin 150 and the European standard. So you can see the impact that one successful job will have on world practice, provided it is published and codified properly. And the other interesting thing, and the contractors amongst you know this, is that there's been a lot of jobs done since then. Center Hill Dam is underway with Bauer. East Branch Dam in Pennsylvania is underway with Bencor Lane. And Bolivar Dam in Ohio with Trevi. And the specifications for these jobs have become more and more prescriptive because the Corps is now saying, we understand what you're doing, you don't need to tell us anymore. So please, we'd like it done this way, and if you can do it like Wolf Creek for half the price, that's great. So that's a big influence on practice. Now, when I was putting this talk together originally, I was going to introduce a fourth topic, which was micropiles. And I soon realized that we simply wouldn't have time, and I didn't want to run over. So what I've done here with my third topic, and we are getting pretty close to the end, Alan, is to make this a little bit briefer and a little bit more of a summary. And I'll run through this a little bit more quickly, because I say I don't want to delay proceedings too much here. The deep mixing methods, many of you know about this from hearing George Phils and the other great specialists talk about this, were developed separately and at the same time in Japan and Sweden in '67. And were introduced to the US, we think, in '86 by Mr. Taki. And I'm not going to show that slide, so don't get too happy about that. So between '86 and 2008, there's a lot of large projects done in the US and Canada using deep mixing. But the market, we always thought, was very erratic in terms of the annual volume. Some years, nothing. Other years, 100 million. A lot of really good contractors in the US from native origins, from Japan, or from the European companies, and always with very keen price competition. And my experience acting for the owner was always that on any one deep mixing job, somebody was way low. Not always the same guy, usually the same guy, but not always. And so really it kind of tore the backside out of the business to a large extent. Now all these applications until '08 were vertical axis mixing, exactly what you think that deep mixing is all about, you know, the big augers and all the rest of it, but relying on traditional concepts, methods, and monitoring. Some of the project outcomes were not really satisfactory. A lot of debate, a lot of unhappiness, differences in expectation between what the owner thought he might get in deep mixing and what the contractor thought he was providing. Neither of these jobs that you see here were anything other than completely successful, incidentally. Just to say, that's Raito's project down at Clemson on the left-hand side using their 6-auger machine. Then what happened? We got Hurricane Katrina, Hurricane Rita in the fall of 2005. And all of a sudden, Corps of Engineers went into overdrive, of course, to repair not only what was going on in New Orleans, but some of the other structures that could be affected by hurricanes as well, such as Herbert Hoover Dike. Now, for those of you who haven't been down there, Herbert Hoover Dike is basically that big hole in the middle of Florida. It's 50 miles in diameter, it's 160 miles around the outside, and on a good day, it's about 12 feet deep. So you can't quite walk across it, but if you had stilts, you could. The problem is that water gets into it 7 times quicker than it can get out in a hurricane, and as the water rises, it causes distress in the very heterogeneous materials from which the dike is composed. So it became a DSAC 1. So in New Orleans and in Herbert Hoover, immense challenges. In New Orleans especially, the challenge of time. We could not let New Orleans fail again. And so all the projects that were in place in New Orleans were up against a tremendous time barrier. And these are huge jobs. 100 rig months, double shifting, millions of cubic yards of deep mixing, the largest job ever conducted outside of Japan at that time. Herbert Hoover. Your task, Jim, if you choose to do it, is to create 21 miles of cutoff, 90 feet deep, through materials that any one section vary 20 times from peat through soil to hard limestone. And, oh, by the way, we want it done in 4 years, please, competitively. So here's just a view of what we're trying to do there. Herbert Hoover Dike on the left-hand side, build that wall through the dike, through all these heterogeneous materials, not to cut off completely the seepage from the lake, because we'd have to go down 200 feet, but as a hanging wall to protect the embankment and its immediate foundation from internal erosion as the lake would rise. And then on the right-hand side, the footprint of LPV, Lake Pontchartrain and Vicinity Contract 111, about 5 miles, 5.2, 5.3 miles of deep mixing to be done to allow the levee to be rebuilt and raised. So who did we have in New Orleans, first of all? There was a contractor, there was a manufacturer who had experience in deep mixing, who could supply a lot of rigs very quickly, had good links with a Japanese company called Fudo Tetra, could provide 8 different automated mixing and batching plants like that, because this was fast track, and had advanced mixing, parameter display control and recording systems, telemetrically sending back all the details to mission control. It's very difficult to mix the soils in New Orleans. And so together with George Fils and Eddie Templeton and the gentleman from Trevi and Solmec, there was tremendous advances made in the technology. So this is what we were trying to do there. And when I say we, taking very minor credit, Fils and I were on the internal board for the contractor, trying to keep him honest. It didn't work. So here's the old levee, which has been degraded. And now the general contractor, AWA, Archer, Western, and Walsh, preparing the working platform. Sorry, Alberici, Archer, Western. And so here's the boys putting in the deep mix columns. Now it always goes like that, doesn't it? Just absolutely painless. So there's the deep mixing in the ground to improve the soil, and some of the soil has the consistency of peanut butter. And so the next stage now is to build a little safety berm there just to protect the work from possible storm surge. Put on the geotextile, and then use the spoil that had been created by the deep mixing. Now, we couldn't call it spoil. That would have been politically incorrect. It was reworked embankment material, which was then used as the heart of the new levee. It's a wonderful engineering material, just terrific. And then after that, all greened up and all nice grass everywhere. It's amazing what you can do for 350 million these days. So that's basically how LPV 111 was done. And the ground had to be improved because it was such a sensitive environmental area, the Bayou Sauvage and all these other places there, that simply they could not permit the footprint of the levee to expand. So what about our colleagues at Herbert Hoover Dike? Remember, we've got to build 21 miles of diaphragm wall very quickly. So what did the Corps do? This time it said, okay, industry, you tell us what you can do. And it had a competition, and 3 people were qualified, each with its own different method. So Trevi came in with the cement bentonite panel wall using the grab and the mill. Bauer proposed the cutter soil mix, which is a very interesting technology, which is basically a combination of diaphragm walling and deep mixing. Been around since about 2003. And then the really interesting one, from our point of view as the panel of consultants, was TRD, trench remixing deep, the continuous wall as offered by Hayward Baker. And that's really what I'd like to focus on for the next and last 5 minutes here. No disrespect at all to conventional walls or the terrific quality of the CSM that Bauer can provide. So TRD, like all these systems with 3 initials, conceived in Japan. Every Japanese technique has 3 initials. And by 2008, it had already been used in over 300 projects in Japan and in parts of China as well. As we'll see in a second, basically it's a gigantic vertical chainsaw that cuts and mixes and can produce continuous walls up to 170 feet deep and up to 34 inches wide. It is really a spectacular piece of equipment. And this is a little cartoon that shows how it works here. So the machine is going to go over towards the left. And as it goes, that big chainsaw, it's called a post, has a big chain running around it, driven under the hood there by a big motor. And as it goes, it's injecting grout through the bottom of the post. and it cuts and rips the material and then reblends it on the upside. So that machine just strolls along, building this beautiful, homogeneous soil bentonite cement wall. Baker had imported this into the US in 2006 approximately and proved it in a nice little job in Los Alamitos Gap in California. Here you see the bottom photograph there is their work at Herbert Hoover, and a close-up of the head and the chain and the mixing. Very effective, very good technique, especially in the very variable conditions at Herbert Hoover. Extremely productive, very quick, high rates of production when the soil permits. So I had written a book back in 2000 for the feds on all the deep mixing methods at the time. And basically, they were all vertical axis techniques. Over on the left-hand side there, either conventional low pressure or jet-assisted, like turbojet. And that was the test columns that were done for a dam out in Kansas. Then along came TRD. So now we suddenly have a different kind of deep mixing method. And then along came CSM and an equivalent called CT-jet, which uses higher pressure. So the world of deep mixing has greatly expanded as a result of these new technologies, which were used with great success at Herbert Hoover. So what about the risk? What did the Corps think? Well, it went about managing its risk by, as I said before, inviting industry to propose. And out of 8 different methods, 3 were selected, and then each of the successful contractors was then bid against each other competitively on different segments of the project. So the Corps got the technology, and they got the competition. They broke down the job into little bits. Well, each bit was still about 3 miles long, right? So it was good work. But then different contractors could work at different parts at the same time. They also had project-specific risk, so very strong verification requirements on the project, including 500-foot demonstration section on every major contract. So we had a chance to look at the stuff, test it, water test it, make sure it was cool before it was then used. As you can tell, this very happy gentleman here on the left works for the contractor. He's just taken another good sample. And although it was a performance specification, the documents were crystal clear when it came to what the goals of the project were. Continuity, homogeneity, and verticality. What the width could be. What the in situ permeability could be. Measured in situ, not on samples in the lab, where all your testing is samples that you've taken in the field. This is in situ permeability monitoring. Satisfaction of a strength requirement, and satisfaction of chemical compatibility with groundwater and soil. So what about risk acceptance in New Orleans? Those of you who have been down there have heard who dat once or twice before. And each of these big machines was named after something from New Orleans, most of which were very rude. So we, in fact, had done a demonstration project with the Corps, Dr. Pete Calley in 2001. But our results were shelved because deep mixing was far too expensive and it was far too new for the old boy network in New Orleans. And so Rita and Katrina changed that. And so the Corps then briefed industry, 2007. Everybody came, was told about the work. And then when this job was bid in 2008, we used early contractor involvement. So the project was actually bid with only 10% completion of the plans and specs. And it was awarded at 35% plans and specs. So as the contractor was mobilizing, the rest of the specifications were being created and agreed as part of this early contractor involvement. What a terrific way to manage schedule. So desk studies. This is classic deep mixing 101, of course, as you know. Bench scale tests, full-scale validation tests in the field, intense monitoring of the production works. That's the project-specific risk. And the performance risk, performance specification, very clear QA/QC. 3% of all the elements cored, not wet grab sampled, cored and tested. So these are all the statistics, but there's several people here who have been involved in that, and they will talk your ear off all night about how good they were on this job. And I have to say, no, even though they say it themselves, very effective use of the contractor's internal advisory panel. We were intimately involved and able to bring the contractor's side technically to the consulting engineer. So there's something you don't often see, those of you who are involved in deep mixing. There's a core that's about 8 feet tall. Normally, deep mixing stuff comes out in 2 or 3 inch little bits. But in essence, all the work that was done at Hoover was done excellently, all finished. All the 3 contractors were finished in early 2012. We learned a lot on the way, especially about heat of hydration and about pressure filtration of the grout and so on. But every single inch of the 21.3 miles was accepted by the Corps. Have we published? You bet. Those of you who are with us in New Orleans in 2012 had the infinite satisfaction, of course, and delight of sitting through a whole session on LPV 111 with 6 papers. And there were 6 TRD papers presented at the same conference, and lots of papers on CSM as well. We're still getting papers on these techniques at the ASTO and USSD conferences, and then it's been published all over Europe and in the ISS MGE bulletin as well. And it's got a chapter in our textbook devoted to dam and levee remediation. So it ticks all the boxes. Now, the other thing is for codification, and we're very close to wrapping up here, is that all these techniques are described in the current manuals by the Corps and Reclamation and DFI, as we mentioned before. So all the existing contractors have their ideas in codification. And now it's permitted other companies, such as DeWind here, with their own trencher, to come in and start doing similar work. So not only is it codifying to protect the quality, it's also encouraging competition to have similar systems, and that's a great thing. And then a lot of these lessons are incorporated in the 2013 manual headed by Mary Ellen Bruce and her colleagues George Fills and so on. So here we have one-pass trenching now developed by other people. Okay, so I really appreciate your patience. We're almost there, and I'm just going to pull this together with a couple of last slides now. So remember I told you right at the beginning that all these views here would come back and haunt you. So this is the one from drilling and grouting. And this is the setup that was used to run the grouting, level 3 setup at Wolf Creek. And here's the Great Leap here. It comprised a group of major developments and processes: materials, technology platforms, design complex. It was implemented under the vision of one contractor consultant team in response to a major market need. It ticks the boxes. It was a great leap. The concrete cutoffs. My thesis says that the Great Leap had 3 steps. The initial acceptance, first of all, that you could actually build a diaphragm wall through an existing dam with minimal dam safety risk. Wolf Creek 1. The development by Solitage and others of the hydromill, fundamental. And then the technological advantages that were made in response to the technical and dam safety challenges of Wolf Creek 2. That's the Great Leap. What we're doing now at East Branch, what we're doing at Center Hill and so on, is almost taken for granted by some people in terms of the quality and the way in which this work is now being done. But maybe that's the way it should be till somebody else comes along with the next Great Leap. For deep mixing, in my opinion, the Great Leap of 2008, inflicted by the Corps of Engineers, was the implementation of a newly imported technology, i.e. TRD, and major enhancements to a traditional technology, i.e. the Trevi Turbo Mix. So there you go. That's my feeling for the Great Leaps. Finally, I would say that each Great Leap was engineered to satisfy the demands of a specific project. There's no question that these would not have happened had the Corps or other private clients not come to the contractors and the manufacturers and said, you have got to fulfill a very rigorous set of requirements. And the leap would not have happened if the demand had not been there. It's all been published, and there is no secrecy. So just to wrap up, and this is where I'm going to go back to my notes just for a second. You probably all know about Karl Terzaghi. And this image here is taken from the seminal textbook, Foundation Engineering, by Peck, Hansen, and Thorburn in 1974. Now, Karl Terzaghi served the Austro-Hungarian Empire. He was an engineering officer in Serbia during the First World War. And on November the 1st, 1915, 100 years ago, he wrote, "War and technology, like fire, are stimulating in their primitive stages, but they degenerate in their eventual achievements." Now, I think we'd all like to think that if he were to somehow rematerialize here 100 years later, November the 1st, 2015, he would agree with us that the technology in his beloved field has not experienced degradation, but has continued to make great leaps as long as there are great challenges to be faced with our profession. The frontispiece of the seminal textbook, Foundation Engineering, by Peck, Hansen, and Thorburn, provides the iconic image, the mature, slightly mysterious Professor Terzaghi hard at work. And the caption underneath this photograph in Peck, Hansen, and Thorburn is quoted here. Terzaghi, 1883 to 1963. He was a young man when we lost him. The founder and guiding spirit of soil mechanics, outstanding engineering geologist, preeminent foundation engineer. Now, I know you can all read, but this is for the benefit of the cameras because I think it's important that this is memorialized. He was the first to make a comprehensive investigation of the engineering properties of soils. He created or adapted most of the theoretical concepts needed for understanding, predicting the behavior of masses of soil. And he devised the principal techniques for applying scientific methods to the design and construction of foundations and earth structures. Now, that image was not taken by my personal assistant, Mrs. Metz, who is with us today, from the textbook, but was sent at my request by a gentleman called Rick Robertson, CH2M Hill International in Panama. And Rick is the leader of the LOX dispute team for the third LOX project. And there's a photograph that I took recently. I do a wee bit of work for Rick on some of the things that he's doing. So he sent it to me with the cover. He's got that photograph tacked up on the wall of the office where we have all the meetings. And it says, pinned up, watching over us in our day-to-day activities and reminding us of the observational method, bringing a smile to my face. You have a colleague, you have a professional engineer up to his neck in alligators in Panama, and that is his guiding light that he sees every morning when he comes down for his Panamanian coffee. So, for me, the real legacy of Karl Terzaghi. An educator, but even more, an inspiration. A scientist, but equally a communicator. Unusual in our field, eh? A genius, but in reality, the ultimate role model for all of us, despite, or perhaps because of, a well-documented love of wine, women, and song. So as I say, no one is perfect. So in putting this together, I've been graced by the help of many of you in the audience. You all know who you are, and so I won't read your names, but it was very kind of you to help me and give me these images, and in fact, in some cases, to review parts of the manuscript. I'd like to acknowledge, and I'd like you to acknowledge too, the wonderful work on the graphics undertaken by Mrs. Metz. Please. The time to prepare this presentation was donated by my family, all of them, but in particular, my wife, Hope. Thank you. My thanks to all of you for having the patience to sit through these beautiful slides and to be so polite and so attentive, and I really thank you very much indeed. And I thank Alan again and Billy for the invitation to give this lecture. It's been an absolutely wonderful experience for me. Thank you very much.